So last time I talked about S-Duality in abelian gauge theories, where the functional integrals, because the action's quadratic, you can actually make sense of, and we proved the theorem modulo some definitions of what the Gaussian measure really meant in infinite dimensions. Now I want to turn to something that's much more problematical, the beginnings of S-duality and non-abelian gauge theories. And it's a theory which isn't well defined. It's simply a theory which you can make conjectures about and then check what might say is the ghost of those conjectures when you can make computations. So I'm going to do some very elementary things, and I'm going to answer some of these questions. Last time I alluded to the fact that what S-duality is supposed to do is interchange electricity with magnetism. That showed itself last time in the star operator. We were really using the star operator very heavily, which, when you do have space-time, does interchange the electric and magnetic field. And I had mentioned earlier that a group in its dual group occurs. That is, the idea is that duality will take one gauge theory with group G and replace it by another one with the dual group, and I'd like to show how that happens. How does supersymmetry enter? I'd love to be able to explain that, but I can only wave my hands when we get that far. And what is the conjecture, and how does one test it? After I go along for a bit, I'll be able to say more or less what the conjecture is, and again be able to wave my hands at how you make tests of it, which leads to some very interesting questions in index theory, actually. So I'm going to follow thanks, Hans. I'm going to follow Montano and Olive, which is one of the original papers that led to the duality conjecture. So what we have is we're going to look at this action functional. This is what we already know, but we're on a 3-manifold, and in fact we're really going to be on R3 for the purpose. And I shouldn't have said action functional, it's the energy functional. I haven't integrated over time. Normally you put in a term like this, which complicates matters. I want to be very simple, so I'm going to simply make the assumption that this term forces, which is that phi has a limit as you go out to infinity of absolute value 1. So here's our usual connection. Here's its curvature. What phi is a map from our 3-manifold, that is a function on R3 with values in the Lie algebra. And d sub a phi means the covariant differential of phi relative to the connection, so it's d phi plus a bracket phi, norm squared. That's what we're getting there. We'll assume that the absolute value of phi is 1 as you go out to infinity, and with a little more, we really want to get a map of the two-sphere at infinity, that is the limit as you go out in radial directions, into S2, the S2 being the set of unit vectors in the Lie algebra SO3, which this forces. As an aside, for later purposes, the S2 in SU2 or SO3 should be thought of in this way. You're choosing a unit vector in the maximal abelian subalgebra. In this case, it's the reals, because you've got a rank 1 group. You act on it by SU2, by the adjoint action, and then the two spheres just SU2 over the maximal torus, in this case a circle. Pi 2 of SU2 over T is the same as pi 1 of T, because by the exact sequence, pi 2 of this is 0 and pi 1 of this is 0. And pi 1 of T via the exponential map from the Lie algebra, that is the line into the circle, this is the same as the kernel of the exponential map, a lattice in T. So phi infinity gives a lattice point in T called the magnetic charge. The generalization of this will be that the lattice of points, which is the kernel of the exponential map from the Cartan subalgebra to the Cartan subgroup, that those points will correspond to magnetic charges in general. So we conclude that the winding number of phi infinity, what's called the monopole number, it is a magnetic charge up to a scale that we'll discuss later. I'm starting this lecture with things that you know, but just said perhaps in a slightly different way. Now I want to consider the equation of motions. Well, we had an energy function. I want to consider the equations of motion. That is a critical point of that energy function, and it's these two equations. And I want to look at special solutions for these two equations. And I remind you of something that most of you know, some of you anyway, that in Yang-Mills in 4 dimensions, where we have splitting into positive and negative two forms, we can write the norm squared of the curvature as the sum of the squares of the self-dual part of the curvature and the anti-dual part of the curvature. And then we can write that as the difference plus twice one of them, depending on whether we want plus or minus. And what we'll get is C2 plus twice this anti or self-dual, C2 being, choose it so depending on whether I have plus or minus, will determine, that is, depending on whether the sector of the SU2 bundle one is dealing with is plus or minus, will determine whether I choose plus or minus. The point being that the action in Yang-Mills in 4 dimensions is a topological term plus this term. And so this is fixed. If I want to minimize the action, I then want to set this term equal to 0. And that's the origin of self-dual Yang-Mills. The same thing here. So we're going to split up this action, or this energy that I wrote. We'll write it as the difference of the two terms norm squared. That will be this term squared plus this term squared, which is up there, plus the inner product of these two terms twice. So I'll get plus or minus, depending on the sign, of this term. On the other hand, whenever you have a star inner product, that means the wedge product of the two. And I put the dot in here indicating I'm wedging the forms and taking their inner product. I'm taking the inner products of their values in the Lie algebra we're talking about. In this case, little SU2. Hard exercise is that this, in fact, is the winding number of phi. So we're in a very similar situation that we had before, that the energy we're talking about is a non-negative quantity plus a topological quantity, except for that factor of g. That's where I said magnetic charge will be some multiple, the coefficient, which will involve over g times the winding number. So we can minimize the energy by writing Fa over 2g, making that non-negative term equal to 0, is equal to this, depending on the charge, the sign of the winding number, just like it depended on the sign of C2 in the self-dual case. Pardon? No. Outside. What I've said shouldn't surprise you, because in fact, if you took this three-dimensional connection and added to it phi, which has values in the Lie algebra, times dt, this is a one form on M cross R, that is a Lie algebra valued one form on M cross R, and you can check that it's self-dual or anti-self-dual if and only if you have satisfied this equation, and therefore they're closely related. It's no surprise that you get the same kind of decomposition as you do in the self-dual case. A monopole is a pair A phi which satisfies the equations of motion. That is a special solution. It's the analog of self or anti-dual that we had before, in which case the energy is equal to, because the other term is 0, is equal to this expression, which you can write down and you can check, see what it looks like at infinity using the equations of motion. So we're going to get g over 2 pi times the monopole number. I'm going to write down, just for completeness sake, a solution with monopole number 1. I took g equal 1 in this expression. Here it is. And one uses it to check properties, for example, at infinity. This is the Prasad-Sommerfeld monopole. There's a 't Hooft-Polyakov monopole. If we'd let that lambda in the action, life is more complicated, but you can write down a corresponding solution, of which this is a limit as lambda goes to infinity. Okay, so I've exhibited a monopole which has magnetic charge. I now want to talk about an object that's going to have electric charge, and ultimately the original Montan-Olive conjecture is you ought to be able to switch the two in a field theory. If the winding number of phi infinity is 0, so it's homotopically trivial, then I'm making an assertion that I don't have time to check, that you can find a gauge transformation so that phi infinity is equivalent to a constant map H. In other words, it's homotopically trivial. I've got some freedom here, which are functions from R3 into the group SU2, which will act on the Lie algebra by the adjoint representation. It turns out you could find such a function. It'll take this homotopically trivial map and actually make it constant. Let's assume that. And I'm going to take this constant. It's some non-zero element of the Lie algebra. It's of norm 1, so I'm going to take it to be the standard element of the Cartau subalgebra. It should really be 1 over the square root of 2. There's a discrepancy between norm 1 and the standard generator you take. So I'm off by square root of 2 somewhere in here deliberately, just because I want to switch from norm 1 to what you normally do in Lie algebras. And we're going to take our phi, which becomes this constant at infinity, and we'll write it as sigma plus phi, where sigma is another Lie algebra valued function, which of course vanishes as you get to infinity. Also, we can, now that we have the Cartan subalgebra, of course we can reduce SU2 into some element, some multiple. This should have been H, this constant, H plus something in the orthogonal complement, which we write this way. It's got to be a skew adjoint matrix. This still should have been H. That is the inner automorphism on this element. Conjugacy by e to the ith on here is just the effect of e to the it on the complex number z and its conjugate. Or put another way, as you should know, if you look at the orthogonal complement of a maximal torus, of the maximal Cartan subalgebra in the Lie algebra, then the torus acts on the complement, splits the space into a direct sum of line bundles, and you have the action on the line bundles via the Cartan roots of the system. I've just looked at the most simplest special case of that here. Once we have this element, non-trivial element in SU2, we can use it to reduce the connection to an abelian connection plus the leftover term. We could write it as A plus tau, because our original, whatever connection we have, has values in the Lie algebra, and because it splits into the Cartan plus the orthogonal complement, we can write it as something in the Cartan subalgebra, in this case one-dimensional, plus the complement. So we write it as A plus tau with this a T connection, so it's just a circle connection in our case, and tau is a 1 form. This should have been in T perp, sorry. I didn't bring down a marker, so I can't make the changes here. And as usual, we write the curvature of f of a plus tau, where this is now abelian, into the curvature of a plus d sub a tau plus 1/2 of tau bracket tau, which, if you think of tau as complex valued, you can easily check that it's this 2 form. So we can think of our original SU2 connection, now that we have split, as being an abelian connection plus an extra field, this form tau, which is really cross-section of the line bundle orthogonal to the Cartan subalgebra. Now what we do is, in this energy, we replace A, the non-abelian A, by A plus tau, where A is abelian, and tau is this other field, and phi by sigma plus H. And I remind you, the way tau was set up, so it lies in this space, and because capital H acts on here, we have that this abelian connection acts on tau, and that gives tau an electric charge, Noether electric charge. Whenever you have an abelian group acting on a vector bundle, the electric charge is technically just the representation you're getting. So for the moment, for us, electric charge simply means whatever the representation that this abelian algebra has, this abelian connection has on the tau. So the idea is you're going to take this object, this energy, and write it out in terms of the abelian part plus the tau, and you're going to replace phi by this constant plus the field sigma, which is a function on R3 with values in the Lie algebra that vanishes at infinity. Okay. I actually wrote a couple, it took me about 3 transparencies to write what you get when you finish doing that, but I didn't think that would be particularly illuminating, so I'm not going to write it out. Somebody wants to see it, I'll show it to you tomorrow. But you can simply write out what complicated expression you get, because I wrote out what the curvature looked like for A plus tau. When you make the substitution, you look at the effect of what you get, and you're interested in these 3 fields. The abelian connection A, the photon, it's got electric charge, all these things might have electric charge, mass, and spin. I'm assuming a lot from you that you should know what mass and spin really are in terms of Wigner and the representations of Lorentz group. Charge really for us means, for the moment, just what multiple of what representation of a circle you get, what multiple of the standard representation. N, if your representation is e to the I theta going into e to the I n theta. The connection has no electric charge, no mass, spin 1 because it's a 1 form. The Lie algebra valued function sigma, what's called the Higgs, in this particular energy where I took lambda equal to 0, it also has no electric charge. There's no representation here. Because, well, you have to, technically mass means look at the representation of Lorentz group. Think of these as time independent, and what happens here is, theorem, for starters, is when you look at these functionals, the mass will be the coefficient of the quadratic term that occurs, where there's no interaction. You look at the quadratic term for sigma in this complicated thing, and look at the coefficient of it. That's the mass. That's how you determine the mass in here. The 1 form tau, what's called a heavy gauge boson, has electric charge G and mass G over 2. If you looked at the expression, you would see that the coefficient of the quadratic term in tau inner product tau, coefficient with no coupling with the other terms, is in fact G over 2. It has spin 1 because it's a 1 form. Pardon?
The mass of the energy boson be proportional to the value of
I don't understand the question.
What's the symmetry break? How does one get the mass of the gauge boson?
Of this thing?
Yeah.
Well, as I say, you write out what I've said. Write it all out, and look for the coefficient of tau inner product tau. The one thing I want to explain now is G as opposed to 1. We're talking about we want a multiple of the fundamental representation for the circle, and I have to say a word or two about that. And this is really a sort of a convention, if you wish. So I'll say a word or two about it. Historically, this is before physicists understood what curvature was, they wrote down that the coupling for the covariant differential with a connection A was given by D, not D plus A, or whatever representation of A you're talking about, but G times A. And they wrote the curvature as dA plus G times A bracket A. So they thought what you really want is something linear without the coupling of A, and they wanted the ordinary, like the abelian case, and there should be some coupling when you have a quadratic term. We know better now that if we in fact wrote A tilde as GA, then what we've called F sub A here is 1 over G times the honest curvature of A tilde, or 1 over G F of A tilde. So then the norm of F sub A squared, which you would normally write down, is 1 over G squared times the actual curvature of the connection you should have. And that's where the term 1 over G squared comes from as a coefficient. It really represents the coupling of your other fields to the connection. There are other ways of talking about that G. So for example, for point charge, the electric field is whatever the electric charge is for that point times this vector, and the magnetic field is whatever the magnetic charge is times this vector. And for the Dirac quantization condition is that the product of these should be 2 pi times an integer. I'm always putting Planck's equal to 1 in my computation. G times A is a connection because you're in flat space, so any convex combination of two connections is a connection. So you could take 1 minus G times 0 plus G times A. What I'm trying to say in a way is you think, from a mathematical point of view, you think of magnetic charge as being C1 for a line bundle, and therefore you'll get an integral of C1 over a 2-sphere divided by 2 pi will be an integer. But for physicists, the actual is the electric charge times our ordinary C1. There's still one further way of looking at it, which is quite useful. Another way of looking at it is if you use Maxwell's equations, etc., then the electric charge is the integral for a large 2-sphere of star 3 times the electric field, and the magnetic charge is star 3 times the magnetic field when you've written the curvature as E times dt plus star 3b. So our basic monopole with winding number 1, if you check back, will have magnetic charge 4 pi over G and electric charge 0. I wrote out the equations for them. You can actually see what happens at infinity, and that's what's involved. For that magnetic monopole, this term is not there, so there's no electric charge. We wrote down what B was, so you could actually see what the magnetic charge is. Now I want to say these things a little differently, purely mathematically, in order to show you where a group and its dual enters. I said this for the simple case of SU2. Let me say it more generally. Magnetic charge, I claim, is a point in the lattice gamma sub G if you start with a semi-simple group, compact semi-simple group G. It's the kernel of the exponential map of the Lie algebra into the maximal torus. And how it arises in field theory is you choose a generic point, omega 0, in the Lie algebra, so that the adjoint orbit of this generic point is G mod T. Where this comes from, remember that absolute value of phi squared minus 1 that I threw out, is whatever energy or action you're talking about will be some function on the Lie algebra. You're trying to find a minimum of that function, and you want the minimum of that function to be a generic point in the maximal torus. That's an example. You could make this theory more general. People have, where you pick other orbits and then life gets a little more complicated. But I want to stick with the simplest possible situation. I only want to show you how a group and its dual appear. And then, of course, phi in phi infinity is an element of pi 2 of G mod T. And because of the homotopy exact sequence, we'll get that that gives you an element in pi 1 of T, which is gamma G. And of course, that'll map to pi 1 of G. We took the case where G is simply connected, so we just had an element in here. Of course, if G is not simply connected, life is a little more complicated, but I won't bother with that now. So magnetic charge, up to this factor G, is just an element in this lattice. Electric charge is a character of T. It's a representation of T on a one-dimensional space. It's given by a character of T. So it's an element of the dual lattice in the dual of the Lie algebra T. And the dual for G times this is 1 over G times gamma G, or I should have had it vice versa, because we want an element in here times an element in here to have one applied to the other should give you an integer. If you want to say this a little better, more traditionally in group theory, what we have is an inner product on the Lie algebra. If we have an element in the dual of the Cartesian subalgebra T, let T sub W be its dual in T. If alpha is a root, after you've complexified the semi-simple Lie algebra, then T alpha turns out is equal to this element. And if R is a set of roots for the complexification, then this set, called the co-roots, the theorem is that it is a set of roots for a semi-simple, another semi-simple Lie algebra, the dual Lie algebra tensor C. And what happens is that if you took the simply connected G, you'll get the corresponding simply connected of the dual divided by the center of the dual. If you started with one with no center, the simply connected group divided by the center, then its dual will simply be the simply connected, the dual groups simply connected. And in between, there are some more complicated things, which is well worked out by group theorists. There's a famous paper of Borel where what I've just said is squeezed into about a page and a half. So, what we've got are two objects. The taus, which have electric charge and no magnetic charge, and the monopoles, which have no, one I exhibited has no electric charge and magnetic charge. Here is what the Montanin-Olive conjecture is. The one-form tau, the heavy gauge boson, has electric charge G and mass G over 2, magnetic charge 0, while the monopole A phi has electric charge 0, mass 4 pi over G, and magnetic charge 1 over G. The mass of the monopole is 4 pi over G. It's because we, in fact, had computed the minimum of the energy, and that's what you get, 4 pi over G. I might be off by a factor of 2 or pi, but I think this is more or less correct. I haven't talked about spin, so let me say a word about that. I found the Montanin-Olive discussion of spin impenetrable. But previously I had observed that the one-form tau, being a one-form, its spin is 1. Whereas if you think of phi, it's a function with values in the Lie algebra. It ought to have spin 0. So you couldn't expect to interchange the two, but actually it's a little more complicated, because in talking about phi and writing the connection A out, it's really the pair, we identified, I won't bring the transparency back, but we identified R3 with the Lie algebra, so there's a kind of SU2 representation and SO3 representation here, where it's conceivable the monopole has spin 1 also. At any rate, I'm leaving it out because that's unclear to me. So, the statement that of Montanin and Olive is because of the various quantum numbers we've described here, there should be a dual formulation of the same theory, should be dual formulations of the same theory, which interchanges G and G dual, so electric charge and magnetic charge gets interchanged, and the coupling constant gets interchanged. G goes into 1 over G. That's a rather startling conjecture on the basis of the little evidence that I presented and that they present. One of the important things here is this coupling constant. It changes a small coupling constant into a large one and vice versa. And so the idea here is that something that you could compute perturbatively in one theory, and you cannot compute non-perturbatively in that theory, when you go to this dual theory, you would be able to compute it because the coupling constant got changed. So something non-perturbative in one theory would be transformed into something which is perturbative in the other theory, which is what made this conjecture so very interesting. So I've at least tried to explain what S-duality, where it comes from in the sense of permuting charges, permuting fields that have electric and magnetic charge, and taking the reciprocal of the coupling constant. In general, the configuration space has components indexed by two integers, dions. This would be something which would have some electric charge, g times it, and it would have magnetic charge, some integer times 1 over g. In general, these will make sense because whatever regime we're in, we're taking the absolute value of phi going to 1 as r goes to infinity. So at near infinity, we have reduced SU2, so the field phi doesn't vanish if you go out far enough. So near infinity, we have reduced SU2 to a U1, and therefore we have an abelian gauge theory out near infinity. And since we define charges in terms of integrals of magnetic near infinity, the charges would still make sense. And SL2Z acts on Z plus Z, and for example, it'll send something, if we think of this as electric charge and zero magnetic, it'll send it into a couple like this as long as these are relatively prime. Okay, now I've been pretty much at the beginning careful mathematically, talking about things some of you know anyway. And then gradually I began talking about some physics involving electric and magnetic charge, which might be new to many of you, but is pretty sort of standard. I mean, every undergraduate knows in physics. Now I really have to start waving my hands. The Montan-Olive conjecture was based on this simple model. Is there a quantum field theory where one might expect S-duality to be true? You want to think of that model as saying, well, gee, it's rather enticing, but can I actually either exhibit or construct a quantum field theory for which there's a ghost of a chance that this interchange between electric and magnetic will really take place? The answer is yes. It would appear that n equal 4 supersymmetric Yang-Mills for SU2 is supposed to be a theory for which this duality takes place. In fact, I stated in my second lecture at the end one consequence or one test of that duality in terms of modularity of a generating function for Euler characteristics for moduli spaces. What's missing for us is the study of supersymmetries, and that supersymmetry algebra that combines the Poincaré algebra with the supersymmetries. That's super-Lie algebra. And that is the algebra that plays a very critical role in this theory. What happens is that you can study the finite dimensional representations of these algebras, and you have reason to believe that one of the representations of this algebra actually is stable and doesn't change under quantum corrections. So it's a semi-classical object. The reason usually behind such statements is an index there. So what's going on here is that you have a Dirac-like operator. I remind you that in my first lecture I talked about a supersymmetry and that it gave you a Dirac operator. Here you'll have a Dirac operator which anti-commutes with these supersymmetries, and that will give you a Clifford-like index. Those of you who know index theory should be reminded of one of the we have various extensions of index. Usually it's an integer, but it can be a difference of two representations. One of the things we did was talk about the case of an operator which anti-commutes with a Clifford algebra, and then that gave you a element in the representations for Clifford algebra. In this case, what you'll get I'm about to state my own conjecture, but I'm pretty sure it's true. That what happens is that if you look at the representations of this algebra, it'll form a certain space, a group, and that will have a Dirac operator which anti-commutes with the representations of this algebra. So you can talk about the index with values in the K-theory for the representation space for this algebra. And the point is, once you do that, is it's stable. And it's because it's stable that you can begin to ask questions in the semi-classical approximation that you can't get to in the quantum field theory. So what's happening then is schematically the following. You've got a complicated configuration space that breaks up into various components, indexed by these two integers, if you wish. Here we have the perturbative theory. We're around 0, and you have perturbation theory over here. You can make whatever computations, a lot of computations, in this 0th component. Over here you have one of these other components, and you have a kind of complicated theory and the representations of the supersymmetry there, etc. You can't touch that theory. You can't touch this theory perturbatively, but because of what I said about stability, you can expect that certain representations of the supersymmetry algebra you'll be able to see on a semi-classical approximation. That's why I drew the tangent space. What does semi-classical approximation mean? You look at the classical solutions in that particular component. That'll form a nice moduli space. You will look at quantum mechanics on that moduli space, and because of the stability of the representations, you expect that what stability of the supersymmetry algebra representation, you would expect to be able to see it semi-classically. And then you have this SL2Z acting, which goes from here to here. You've made your computations over here, so you can make a conjecture as what to expect semi-classically over there. So if S-duality holds, you have a conjecture that you can talk about mathematically. Here's an example of what happens. The moduli space MM of SU2 monopoles of magnetic charge M, it turns out it's a beautiful space, originally studied by Mandula, I think, and then some beautiful papers by Atiyah and Hitchin. Of magnetic charge M is the orbit space under a cyclic group of order m of a simply connected space of dimension 4 times m minus 1. Let HR of M be the space of L2 harmonic R forms on this space, and split the harmonic forms into a direct sum of pieces on which this generator of the cyclic group of order M acts like C to the E. Magnetic charge, relative, and electric charge, really. Sen conjecture that the cohomology of this space is 0 unless you're in the middle dimension. And in the middle dimension, this will be C if these two numbers are relatively prime. That's getting from an action of SL2Z, really. And 0 otherwise. In fact, in general, the conjecture is that SL2Z acts on the direct sum of these spaces. And of course switches this to integer index. There are proofs of these conjectures for m equal to 2, and they're usually done because you know the geometry of the space very well. And so you compute the index, which is not so easy. You're talking about L2 cohomology, so that's kind of hard to compute the index. You either, well, usually you look at it as a boundary value problem and see what happens near infinity. And you have a vanishing theorem, and the combination of the two gives you the dimension count you want. This has been souped up to other values of Q, but you can see that you've already got an index. You got an industry going on of verifying tests of the S-Duality conjecture by computing the index of the Dirac operator, or the dimension of a space of harmonic forms, which comes from knowing it in the perturbative regime where you can get your hands on it, and then expecting that duality is going to tell you what the answer looks like in a component that you can't touch by perturbative methods. Well, I think I'll stop there. One final comment. I've got one more lecture to give on Thursday. I have really two choices. One is to continue talking about supersymmetric Yang mills. For example, I could write down, which physicists don't usually do, what the action is for supersymmetric Yang mills, perhaps describe the supersymmetry for you. For n equal 1, 2, 4 supersymmetric Yang mills, I could show you what the supersymmetry algebra looks like. That would take me an hour. The other is to talk about another kind of duality, T-duality, and give you a simple example of that. I would love some feedback on that tomorrow, and I'll decide Thursday morning on the basis of feedback tomorrow as to which of those two lectures to give.
I'll write up both of them over here and keep one to the side. We can make copies of them.
Well, thank you. Questions? Yes.
So you haven't said anything about strength today, but I guess from the SL2Z invariant, they're lurking in there somewhere. Can you say something about?
No, that's something I'm trying to learn now. Certainly, the most recent developments is to say the best way of looking at how SL2Z appears is through string theory. And it's because that is, one way of looking at it is, although you're talking about a 9-1 Minkowski space, you really want to add in a 2 torus and look at a 12-dimensional space. That 2 torus will be 1, 1. And look at a 12 that is a 10, 2 Minkowski space. And that's where, so-called F theory, that's where everything is really going on, and that this SL2Z is coming out of the usual SL2Z associated with a torus. All those are just, I'm just reporting what I've been told, and I haven't carried out any computations to convince myself that that's where the SL2Z is coming from. But that's one example of a number of different statements that are made as to where the SL2Z is coming from. There's another point of view of SL2Z that you need a little more physics to understand, and it's something like, if you look at the pair of integers, take 2 such pairs, the symplectic, so if you had A1, A2, B1, B2, A1, B2 minus A2, B1 is a natural invariant. So what you're going to have is invariant under SL2R, because you've got a symplectic invariant. But now you've got integers. You've quantized, it's discrete, so the natural invariant is SL2Z. That could be pushed to give some explanation of why you have SL2Z. It's another one. There's a third, but I don't think, mathematically anyway, we have a clear understanding of where SL2Z is coming from. Yes?
You're always talking, this last part of it, you're looking at the Minkowski space of the signature 9-1 and then add on this and get 10-2. Am I correct? Now, some algebraics also talk about lattices inside these lines. Namely, lattice in the usual sense, but because the signature tells different.
Signature what?
The signature 10-2 tells different.
Yes.
So you repeat or summarize?
Well, there's the question, yeah. The question is, I'm trying to understand something. Namely, in the situation of 10-2. Okay, is that true?
Well,
I'm trying to understand this question about why.
what you're saying is that it is natural, coming elsewhere, are lattices of signature 10-2 inside of a 10-2 Euclidean space. They do come up. They do come up because when you take these string theories and you compactify these string theories, what that means is you replace your space, say 9-1, by 3-1 plus a compact 6. Or you may not have a compact 6, you might have a compact 4, and then you would have 5-1. Okay? But so if you compactify by a torus, and you ask yourself, what are the moduli spaces? What parameters you allow to free? You'll frequently find the lattices of the character group, really, of these maximal tori entering. So, especially if you're going to put in this 2 torus of type 1-1, I can see that if you compactify in the right space, the lattice of the character group will appear as a lattice somewhere. And often enough, in fact, in the dualities. In the dualities between different theories. So you'll say, even though this doesn't make any sense, it'll give you the flavor. I'm going to compactify a type 2A superstring on such and such a space, and it should be dual to a string theory of type 2B compactified on another space. Since we don't know what these things mean, you can only check certain ghosts of the field theory. One of the things you check is the moduli space vacua of the theory. And in that checking of moduli spaces of vacua, these lattices frequently appear. So the test of duality will often be, well, at the appropriate moduli space of classical solutions or quantum solutions of vacua is the same for this theory and that theory. It's much in the flavor of what I've just said. We don't know what the field theory is. We only have a very small amount of information that we garner about the field theory. We, I mean the physicists, have. And then you just check whether that information is consistent with what the conjecture is. But frequently in these lists you will find all these lattices appearing, and self-dual lattices appear, other lattices appear, and the point is that it's striking. These are striking confirmations because you wouldn't expect to make these kind of computations and end up with these two vacua, these two spaces looking alike. It's kind of a surprise to see that happen. So I want to emphasize that even though I say there's very little that one can check, the evidence is pretty striking. Because you get things that you don't, to be true, that you had no clue to, and that you don't expect. So if you're right in there with the material, all sorts of things are happening that the simplest explanation is that that the duality has some real deep meaning, even though the field theories or the string theories for mathematicians aren't well defined. Yes?
What's the current status of this conjecture about L2 homology of moduli space? I know this has been checked in a few cases. Have they done it in general yet, or the one that's written on your
No, I don't think it's done in general. Graham Siegel may have proved it. Yes, I think Graham Siegel has a proof of this conjecture.
Excuse me. So in the last lecture you showed us that if we start with a Riemannian manifold, four-dimensional Riemannian manifold, we can get a modular form in a certain way. Do we know the coefficients of this modular form in terms of invariant for the format?
I don't.
Is it known?
No.
The other question I have, if you look at the duality between Knowlson theory and Seiberg-Witten, the dual of SU2 is S1, whereas in your case, the dual of SU2 is SO3. Is that duality different with these?
There is no strict duality in the n equal 2 supersymmetric theories. You have to have n equal 4. And one really shouldn't say that the Donaldson-Witten Lagrangian, the one that gives you the Donaldson invariance by definition, is dual to the Seiberg-Witten. Something else is happening there with renormalization group techniques, and it's not this duality. Again, if you go to string theory, it is said that you can see where the duality really lies and why you're going to get Seiberg-Witten. But I've looked into that enough to feel that it doesn't supply enough information. It doesn't really tell you these two theories are the same in any way.